Yeah, second period ran out of battery power. GoPro batteries are garbage. So,
we're not watching.
anyways, yeah. All right, so guys, ladies and gentlemen, again, the microphone's behind the camera, so it catches everything that goes on in the room now. I don't have my little lapel mic anymore. So, let's continue talking about calculations with equilibrium. And you want to do calculator, you need to basically take an active role in your learning today. You need to actually go and do the work. You can't just watch me. You need to practice and practice and practice.
Always.
Because this is probably one of the more challenging units, and it's a very small unit too, but it's still a very challenging unit because of the math and the algebra and figuring out what it means. So, with that, starting from where we talked about equilibrium expressions, we remember that in equilibrium, we have a forward reaction and a reverse reaction occurring at the same time. And when you've reached equilibrium, the rate of the forward reaction and the rate of the reverse reaction is the same. Now, that's just the rate of reaction, like the speed of the reaction. It doesn't talk about the concentrations of the products and the reactants. For that, we have our KEQ. So the KEQ comes from our equilibrium equation. In this case, A and B are in equilibrium with C and D. So we take this information and we make our KEQ. The KEQ is always the product concentration over the reactant concentration. So in this case, concentration of C raised to C, concentration of D raised to D, over the concentration of the reactants raised to their coefficients. It's also important to remember that if you have an aqueous system, you only show aqueous things. There's no screen on the back. Anyway, so
Just look at how you secured it.
voodoo magic. No, magic. Accio magneto. Anyway, so it's important to remember that if you have an aqueous system, then everything in your equilibrium expression should be aqueous. You only show aqueous things. You don't show solids, you don't show liquids, you don't show gases. If you have a gaseous system, then the only thing you show are gases. Okay? No solids or liquids or anything like that. For now. Later on, you can learn how to gel them together, but not in this class. Yeah.
So when it's aqueous, is it whenever there's like a liquid present, or like how do we know?
If you have ions, they're aqueous.
Okay.
So basically, ions, only ions. Yeah. And then aqueous things that are dissolved. No liquids. So either an aqueous, a thing that is dissolved, and AQ after it, or ions. Does that make sense?
Absolutely.
Okay, cool. So, yeah. Now in this case, you actually look at the diagram where we have A and B getting used up to produce C and D until they reach an equilibrium state. In this case, there are more C and D present than A and B, so the numerator would be larger than the denominator. This is the case where you'd see a KEQ that is larger than 1. When it's larger than 1, we say it is products favored. It simply means there are more products present than there are reactants present. If the opposite was true and the denominator was larger, we would say it would be reactant favored. There's simply more reactants, A and B, than there are products. Okay. Sound familiar? Any other questions? Give me a thumbs up if you're ready to move on. Moving on. Okay. So then, yesterday or last time, we practiced writing equilibrium expressions from the equilibrium equation. So in this case, you would turn this 2 and this 2 into exponents. Where you have an SO3 in the equilibrium expression, this would be K equals SO3 because it's a product with a square. And the SO2 in the reactant would be SO2 with a bracket and a square and O2 with brackets. Okay. Now, if you take chemistry AP, we'll actually change the brackets and we'll use pressures instead. But in this class, everything is just going to be brackets. And what do brackets mean? Concentration in what unit? Molarity. Concentration in molarity, which is moles per liter. So when you see brackets, we're talking about molarity, which is moles per liter. And of course, we can go the opposite direction too. If you see a square in an exponent, basically this means that this should be a coefficient as a product. So HI squared becomes 2HI. Okay. And every now and then you find a situation where there's something missing. In this case, water is missing. It's not shown here because water is a liquid. And that brings us to what we did yesterday. Yesterday we took the KEQ and we said, all right, now that we have the equilibrium expressions, we can plug concentrations in, and once we know what those concentrations are, we can either solve for the KEQ if we have the concentrations, or we can solve for an unknown concentration if the KEQ is given to us. By the way, this KP means equilibrium pressure. It's only used when you have gases. That's why it doesn't say KEQ. Okay? So you can plug the both numbers in and solve for KEQ, or you can use the KEQ and solve for an unknown concentration. And that's what we did yesterday. Questions? If you were not here yesterday, I strongly recommend you get on YouTube and watch the video. Get on Google Classroom, the link to YouTube, and watch the video because this is very, very valuable. Okay. Then we talked about solubility product constant, and solubility product constant is a number that says this is the maximum upper limit of ions that can dissolve. So you can only put so many of these ions in solution. That's the maximum upper limit. And it comes from the dissolution equilibrium equation. So here's a great example. Silver chloride is in equilibrium with silver and chlorine. So the KSP would simply be the concentration of the products, silver and chlorine, over nothing. Why is there no denominator in the KSP? Because it's a solid, exactly. The reactant is a solid. You wouldn't have a solid in there, so there's no denominator because there's no non-solid reactants. The only reactant that's there is solid, so no denominator in KSP. KSP always has this value, or this setup. And this number, 1.8 times 10 to the negative 10, tells us that is the upper limit, that is the maximum number of those ions you can dissolve. All right, now this one, this equation, if you look at it, for every silver chloride molecule that dissolves, how many silver ions do you get? One. How many chlorines do you get? One. So for every X concentration of silver chloride, what's your concentration of silver going to be? X. What's the concentration of chlorine going to be? X. Now, when you plug it in, this just becomes X and X, so this becomes X squared equals that. X times X. Okay? Makes sense so far? Now, with calcium fluoride, the situation's a little bit different because every time you dissolve a calcium fluoride, you get one calcium, but you get two fluorines. So every time you dissolve X calcium fluorides, how many calciums do you get?
2X.
You get X. How many fluorines do you get?
2X.
You're going to get 2X. And then when you plug them into the equilibrium expression, this is going to be X, but this is going to be 2X. And 2X squared, what is 2X times 2X?
4X.
4X cubed. So what happens is this becomes 4X, this is 4X cubed, 4X cubed becomes the KSP value. Make sense? We're going to use that here in a second. Then we talked about QSP. QSP is the concentration of ions you have right in front of you at any given time. Okay? It's not KSP. KSP is the upper limit. QSP is what you have in front of you. If the concentrations of ions is less than KSP, what is this solution? Unsaturated, exactly. If the QSP is less than the KSP, you have an unsaturated solution. If the QSP is equal to the KSP, it's saturated. And if the QSP is larger than the KSP, supersaturated. And that's where solids come out. So what we're talking about today is we're going to talk about, can you make this solution? And when we talk about can you make it, we're saying, is the QSP you want to make bigger than the KSP or less than the KSP? If you want to make a solution that has a QSP that is less than the KSP, you can make it. If you're trying to make a solution that has a QSP that is more than the KSP, you can't make it. Make sense? Yeah. All right. Then we did an example exercise, and that's what we are doing today. All right. So you also noticed that the test was moved to Tuesday. I have a test review worksheet we'll do on Monday, and we're going to do the videos on Friday. So that's our breakdown. Practice today, in-class worksheet Wednesday, in-class worksheet Thursday, videos on Friday, review worksheet on Monday, and the unit test on Tuesday. Yeah, it's a lot of busy work, but practice is the only way you can do equilibrium exercises. All right, here we go. Any questions about that before we move on? Yeah.
Can you go back a slide? So when it's the QSP is less than the KSP, that's when it's saturated?
Unsaturated.
Unsaturated.
Basically, this tells us when the QSP is less than the KSP, this is telling us that there is more room for ions. The ions we want to put in still have more room for more ions. So the QSP is the ions we have, and the KSP is our upper limit. All right. So, practice calculations. If 0.0034 grams of silver chloride is added to half a liter of water, will it dissolve? Well, we have to remember what our KSP is. So our K, oh, I forgot to buy a pair of new pens. Is it really nice? Because all my pens are like almost dead.
I got like a pack of 4 of them.
Oh. Then you keep it. Although the school pays for them, so I just need to go back and get them. I forgot to pick them up. So if you can't see it, let me know. If there's too much later, let me know. All right, so we have a KSP for silver chloride of 1.8 times 10 to the negative 10. And we want to know, if we try to dissolve 0.0034 grams of silver chloride into half a liter of water, could we do it? That's what we're trying to figure out. So we remember that silver chloride, AgCl, solid, will be in equilibrium with the silver and the chlorine, and this KSP is going to equal the concentration of silver multiplied by the concentration of chlorine. So what do you think we should do with that 0.0034 grams of silver chloride? Convert it to moles. There's nothing we can do with grams, we've got to use moles. So we'll take our 0.0034 grams of silver chloride, and we're going to convert that into moles. For every 1 mole of silver chloride, there's going to be so many grams of silver chloride. And this is the part that you take an active role in your education. So copy down, bang out the numbers, I'll wait for you. Extremely small. Yeah.
Where does the 1.8 times 10?
Book value. So I got it in the previous, I wrote it down on the previous slide here. But yeah, it's a book value. Somewhere someone calculated, measured it, and then they wrote it down, and we assumed it was right. Silver is 108, chlorine is 36, 145 more? Round up, round down. Yeah. I can round down if you want. Would you rather, you'd like to round down? Just round down. I know you're feeling like you're not comfortable with 144, so there you go.
Cool, I didn't.
She said,
Oh yes, that is a superior blue pen. All right, so 0.0034 divided by 143. So how many moles of silver chloride are we trying to dissolve?
Oh, dear God.
2.4 times 10 to the negative fifth? Okay, negative fifth moles of silver chloride. So in attempting to dissolve 0.0034 grams of silver chloride, what we're really trying to do is dissolve 2.4 times 10 to the minus 5 moles of silver chloride. How can I use that number? I'm going to dissolve it in 0.5 liters of water.
Divided by a half.
Exactly. So the molarity of our AgCl solution is going to be 2.4 times 10 to the negative 5 moles divided by 0.5 liters. That's going to give us the concentration of the solution that we're trying to make.
Is this what we did like a couple weeks ago? The molarity?
Yeah, though, yes, we're using the molarity exercise, yeah. Molarity is still mole per liter. Everything builds on itself. Everything we learned in this class has a purpose for the future. Okay, so hopefully we got 4.8 times 10 to the negative 5 molar. So this is the concentration of solution we're trying to make. So our KSP basically tells us that we can make a solution with a KSP of 1.8 times to the negative 10. Now here's the important thing and probably the trickiest part. For every chlorine, you're going to get a silver and a chlorine, or sorry, for every silver chloride, you're going to get a silver and a chlorine. It's a 1-to-1-to-1 relationship. Which means if this is 4.8 times 10 to the negative 5 molar, then silver must be 4.8 times 10 to the minus 5 molar, and chlorine must be 4.8 times 10 to the minus 5 molar. So you take that number and you plug it in right there. So we're going to have a QSP that's going to be 4.8 times 10 to the minus 5 multiplied by 4.8 times 10 to the minus 5. So if you take these, basically you make a solution of silver chloride, you're going to get a QSP of this, because it's a 1-to-1-to-1 relationship. Plug the numbers in, and we're going to compare our QSP to our KSP.
Is this what the worksheets are doing?
Yep. Well,
Like
the first worksheet
all
only
of
has
this work
one
right
of
here?
these tomorrow. The second worksheet has 2 or 3. Third worksheet has all of them.
Should we multiply them?
Yeah. Or square them. You can choose. Just don't multiply them by 2.
2.3. 4. 7 times 10 to the negative 9.
So 2.3 times 10 to the minus 9?
Yep.
Okay, so this is the QSP. This is what we are, if we could calculate the amount of ions and concentration, this is what we would get if all those ions would dissolve. Now we have to ask ourselves, is this bigger or is this bigger? What's bigger, 10 to the negative 9 or 10 to the negative 10? 10 to the negative 9. So we have a situation where our QSP is now larger than our KSP, and the question says, will it dissolve? And the answer is no. It will not all dissolve. We are trying to squish more ions than God said we can. God says 1.8 times 10 to the negative 10, and we say we'd like to do 2.3 times 10 to the minus 9, and it's like, nope, this is too much. We're trying to squish too many ions into solution. Does that make sense? Okay. If you have a question, now would be a good time to put your hand up and wave it around. Question?
So how is the K that's is that like just a standard or?
Yep. KSP is a constant. Big K values in science are constants. It is a constant upper limit for that chemical at a specific temperature. Now, obviously when temperature changes, the KSP changes, so it's only constant at a specific temperature. And since I brought it up, what do you think happens to the KSP if the temperature goes up?
Goes down. It increases.
It increases, exactly. Because with a solid in a liquid, you can dissolve more stuff as temperature goes up. So that means your upper limit goes up. So if you increase temperature, KSP will also increase. That's not going to happen in this class. I don't even know what's going to happen in chemistry AP, but we just basically say it's a constant for this reaction. Okay, so give me a thumbs up if you're ready for level 2. If level 1 you're comfortable with, ready to move on level 2, give me a thumbs up. We're getting there. Any questions?
No,
You just
I
need
just
more practice?
Yeah.
Perfectly fine. Okay, level 2. do it over on that side. If 0.0019 molar of fluorine is added to 0.0034 molar of chlorine, will a solid form? So for this, I'm going to need to get the book value for the KSP for calcium fluoride, and that book value is 5.3 times 10 to the minus 9. So the KSP for calcium fluoride is 5.3 times 10 to the minus 9.
You'll give us the values, right?
Unless your exercise is solved for, yes. So if you ever need the KSP, you'll be given it unless your exercise is solved for that.
Right.
Okay, so calcium fluoride. When calcium fluoride dissociates, it dissociates into a calcium ion and 2 fluorine ions. Cool? You can see how this equals this?
Yeah.
Okay. So that means the K value, the KSP, is, remember, KSP is always going to be a positive thing and a negative thing. Everything in this class is binary, one positive thing, one negative thing. So what goes in this box? Calcium. Yeah. Calcium. What goes in this box? Fluorine. And there's one thing left to finish that KSP.
Exponent.
Yeah. 2 here becomes a square there. So this is the KSP expression for the dissociation of calcium fluoride. There's your calcium, that's your positive. There's your fluorine, which is negative. This 2 coefficient becomes a square up here. Give me a thumbs up if you can see why the square is there, if you understand this. All right. So what's next? What do I do next? Find our QSP by plugging the numbers in. So do that. So you got a concentration of fluorine, you got a concentration of calcium. Find a QSP. So your QSP, I'll just actually do that down here too. Your QSP is going to be the concentration of the calcium and the concentration of the fluorine. Don't forget your square. So do that now.
Question.
Yes.
Will the KSP always be given?
Okay, so will the KSP always be given? It will be given unless your goal is to find it.
So like you could be given a QSP and have to find a KSP?
No. If you're going to be finding a QSP, you'll be comparing it to a known QSP.
Oh, okay.
What they might say is, you dissolve this amount, what is the KSP? And then you, in the case, multiply, solve.
Okay.
Like what you're doing now. Yeah.
So are the brackets, can we like look at them like they're parentheses?
No. A bracket specifically means, oh yeah, for math, for algebra, yeah.
Yeah.
For algebra, you can think of them as parentheses.
Okay.
But you need to realize that when you see brackets, that means concentration and molarity.
Okay.
No, you're making me nervous. Are you using your personal technology?
Not exactly.
He's punching his leg.
Are they?
Why are you punching?
I wasn't punching, I was just chilling here. It's kind of weird.
It's all right. No, it's okay.
You know.
Happens to me too. If I sit down for a long time, it feels like there's cement in my veins. Like, make it stop. Is that what's going on?
Yeah, that's it.
Yeah.
That's it.
Okay.
Happens to me too. Sit down too long. Such a stupid system we have. Like, let's have teenagers sit down for 6 hours a day.
Honestly.
Could you imagine having to stand for 6 hours a day?
I would like that.
I would like
That's what he
standing
does.
desks.
It's just something to
Well, and then we don't have to do PE all the time either.
make the campus really long. There needs to be a track. You have to like run. You have to run around the track between each class. Okay. Do you have an answer for me? Do you have a QSP? All right. So we got our calcium concentration of 0.0034. We got our fluorine concentration of 0.0019. Don't forget to square it. And your QSP ends up being what?
1.2 times 10 to the negative 8.
1.2 times 10 to the negative 8? Does that sound good?
Yeah.
Do we have a consensus?
Wow.
Okay. And this unit is going to be molar cubed. Molar cubed. Cool, huh? You understand why it's molar cubed?
Yeah.
This is only relevant if you're taking chemistry AP next year. But if
It's
it
like-
is, it's like an easy, very easy multiple choice question. Okay, question.
How is 1.2?
That's what she said it was. 0.0034 multiplied by 0.0019 multiplied by 0.0019. Did you get a different number?
Oh, I only forgot.
No square?
Yeah.
The numbers are small, but they're significant. Okay, so this is our QSP. So the question is our QSP larger or smaller than our KSP?
Larger.
This is 9, by the way. 9. Yes?
So why is that in
Oh, because concentration is molarity. So you basically have molarity multiplied by molarity squared.
Okay.
So molarity cubed. Again, not relevant in this class, but will be relevant in AP. Okay, so is the QSP smaller than or greater than our KSP?
Great.
Greater than.
It's greater.